Okay, let's get started. Can people in the back hear me? Great. So today we'll continue to talk about the single stage equilibrium process. So before I dive into today's content, let's do a quick recap of what we have learned in our last lecture. So in our last lecture, we talked about the TXY diagram and the XY diagram in details. So in normal TXY diagrams, so we basically have a temperature as a function of the mole fraction, either in the liquid or vapor phase. And this plot is basically can be divided into three kind of like sections or three parts. So we have two lines here, and the bottom line is the saturated liquid line or the bubbling point line. And this top line is a saturated vapor line or the vapor, the vapor point line. Sorry, the dew point line. So below this line, we have a supercooled liquid, and above this line, we have a superheated, overheated vapor, and in between, we have two phases in equilibrium, right? So, if you have such a separation unit, right? If you have a feed coming into this separation unit, then basically depending on the temperature, right? And this is a binary mixture. Depending on the temperature, in this separation unit, you could have a single liquid phase or a single vapor phase, or a saturated vapor coexist with the saturated vapor, right? In that case, we can, from this TXY diagram, we can find out the composition of your saturated liquid and saturated vapor just by drawing a horizontal line here, right? This horizontal line represents the temperature that will cross with these two lines. Then the points give you the composition of the saturated vapor and the liquid. Okay. And as we will tell later, and this separation unit, this separation process is called flash, because typically we have a liquid stream, right, coming in, and then we can just either reduce temperature, either reduce the pressure with a valve or with a pump, or increase its temperature by adding heat so that we can partially vaporize the liquid, right? And this process is called flash. Then we can, if the relative volatility of the species are different, then we will be able to get a vapor phase whose composition is much different from the liquid phase. That's how we do the separation. So we also talk about the Q line on the XY diagram. But before I recap that, we can kind of quickly recap. For such a system with extensive variables, we've been able to compute the number of degrees of freedom, right? Which is say +4 for a binary system, right? And we have degrees of freedom of 6, right? In this case, we can set these. Typically, we can set the temperature, pressure, and the flow rate of the feed, and the pressure of the separation unit, and C-1 of the composition. That way, we can fully define the system. So now, what we need to pay attention here is that, on the variable end, we have the composition, we have the flow rate of the feed and the acceding streams, we have the temperature of the feed, temperature pressure of the feed and the separation unit, and as well as the heat. On the equation side, we have basically three, or maybe 4 category of equations, right? These are mole fractions you sum to 1 in each phase. These are equilibrium condition, and these are mole balance, and these are energy balance. And then we discussed the Q line, right? So we derived, Q line is basically this line here. It represents I mean, the way we derive it is we start from mole balance for each species and overall balance, and then we can derive an equation that correlates YA, that's a vapor phase composition, with XA, that's a liquid phase composition. And we discussed this represents a line that starts from a point on the 45-degree line, right? And the exact point where it starts from depends on the fate composition, right? Which is and the slope of this line depends on the the so-called molar vaporization ratio, right? And we talk about for such a system now, for this system now we if we set TF, PF, PF, and so basically because here is a binary system, if we set ZA, then this whole system is defined, right? The way we do this graphically is to start from the ZA, find this point, draw this line, and this line cross with this equilibrium line, and this intercept gave us the composition of the of your vapor and liquid phase in the separation unit. Right? That's how we do it. But now the question is why? We know this graphically we can solve this problem, but now the question is why we can do that, right? Fundamentally, why this graphical method can give us the solution we want. Any guess? So kind of like using this is not difficult, but I guess we also need to understand why if we do this, we will get the solution, right? So the answer here is that, I mean, if you look at these two lines, right? This X and this black line, that's the equilibrium curve, right? We know that the equilibrium curve basically gave us all the points, So first of all, on the XY diagram, any point on the equilibrium line gave us a composition when for a binary system, for a binary liquid vapor phase system, that every point on the XY diagram gives us the composition, the equilibrium composition of the liquid and vapor phase, and also it has the information of the temperature, right? Which is to say that every point on that line gives us, if you do a horizontal line here, you will get 2 points, right? Those 2 points will be plotted on the XY diagram, right? And on the other hand, this Q line, as we developed it, right? This represents in this separation unit all the possible composition in the vapor and in the liquid and vapor phase that will satisfy mole balance equation, right? Because we derive the Q line from the mole balance equation. That means any point on this line satisfy this mole balance equation, right? Now if we go back, just discussed, right? Once we specify these variables, then we should be able to fully define this system. And then when we fully define the system, the variables should satisfy these equations, right? And like I said, there are several equations. First, you have equilibrium condition, right? And second of all, you have the mole balance, right? So basically, if you combine this with this, that gives you the F equals V plus L, right? That is to say, now we have two curves, and the cross of that two curves give us a composition that will automatically satisfy the equilibrium condition, right? K equals Y over X, as well as the mole balance, right? So that's why this point gave us the solution. Questions? So next we will talk about azeotropes in binary system. Azeotrope is kind of a special type of mixture that will have quite distinctive features compared to a normal zerotrope system. So this is the TXY diagram of a normal zerotropic system where both the bubble point line and the dew point line, they change with the composition monotonically, right? If you start from a high boiling temperature phase, like a high boiling temperature component, then both of these lines will decrease as a function as you increase the mole fraction of the lower boiling point component. Whereas in an azeotrope, right, there are two types of azeotrope. There are maximum boiling point azeotrope system as well as minimum boiling point azeotrope system, right? Now, in this figure, what we show here is a maximum boiling temperature azeotrope system. So the feature here is that if you look at this figure, the bubbling point line and dew point line, they do not change monotonically with the the mole fraction. Well, instead there will be in this case there will be a maximum, right? And this maximum point is the azeotropic point. And at this point, the dew line actually, the dew point and the bubble point, they just kind of overlap with each other, pinched at that point. In other words, at this azeotrope point, okay, your vapor composition will be exactly the same as your liquid phase composition, right? So your K value of both A and B are 1, and the relative volatility is 1. So that if you boiling a liquid at this azeotropic point, you will produce a vapor with the same composition. Therefore, there's no way you can separate them by just partially vaporizing them or partially condense them, right? So the best you can do is that if you start from for example, if you start from a composition here, 0.2, let's see, this composition is in between the pure phase of A and the azeotrope point, right? The best you can do is if you do the flash operation, the best you can do, you will produce a vapor. So you will separate these two species. The best you can do is to get a pure A phase and azeotrope point phase, right? So you cannot go across the azeotrope point. So, and why we have such a kind of interesting behavior. Physically or chemically, it's like when you have two components, two species, they are different chemical type, but with close boiling points. They will have this behavior. And at the azeotrope point, it's kind of like these two species chemically they want to be with each other, so that you have to give more energy, to just boiling them, okay? Instead of compared to just boiling the pure phase, right? They like to be each other. Then there's also minimum boiling azeotropic system that just looks opposite, right? In this case, you have a kind of concave dew point line and bubble point line. Here you have a convex dew point and bubble point line. Again, these two dew point and bubble point line, they do not change with the mole fraction monotonically. There will be kind of a cross point here, and that's the azeotrope point. At the azeotrope point, the liquid composition is the same as a vapor composition. You won't be able to separate them. And in this case, at the azeotropic point, the boiling temperature of the azeotrope is lower than the boiling temperatures of the pure phase. That means your component A and B, they just doesn't want to be with each other, right? So as long as you input a temperature that's lower than the boiling temperatures of each of the constituent phases, they will boil, right? The mixture will boil. right? We can also look at the, this is the PX diagram we discussed in our last lecture. So these two lines are the partial pressure of the component A and B, right? And here is A is isopropyl alcohol and the B is isopropyl ether. So the total pressure curve looks like this, right? And we know that if we draw a straight line between this point and that point, that gave us a system, that ideal system, right? Satisfy the Raoult's law, right? But in this case, this is a non-ideal system. For non-ideal system, in this case, we have a positive deviation from the Raoult's law. And this positive deviation can be described by the modified Raoult's law, in which we introduce activity coefficient just to describe this deviation. And in this particular case, because the pressure is higher than the pressure of the straight line here, so your activity coefficient are greater than 1. And this maximum pressure point is where the azeotrope point is. Okay, and we can also look at the XY diagram for such an azeotropic system. And interestingly, as you can see, so we know for a normal system, the XY diagram would be either concave, right? That's like this, or convex, that's like this, right? But in this case, as you can see, the shape changes, right? Cross this 45-degree line, and then change from concave to convex, and this point is the azeotropic point. Okay. So, needless to say, at this point, we have the relative volatility to be 1 and key values of each of the components to be 1. So, and that's kind of the TXY diagram. So now, when we deal with azeotropic system, right, as we just discussed, I mean, it's kind of hard for us to separate them, because if you start a composition in this region, the best you can get is this point and that point. So you might be able to get pure phase A, but you won't be able to get pure phase B, right? You will get an azeotrope. That just makes the separation process hard. In some examples, right, in some systems, the behavior of the system could change if you change the temperature, right? So, for example, for ethanol water system, ethanol water azeotrope system, right? If you reduce the temperature, the pressure from 1 atmosphere to less than 9.3 kilopascal, then this azeotropic point will shift to one side and disappear, and your system will convert from an azeotropic system to a normal system. Then you will be able to separate them. Okay. And for maximum boiling azeotropic system, the PX diagram looks like this, right? In this case, the total pressure is concave, that's below the straight line, right? And in this case, similarly, we can use modified Raoult's law to describe this behavior, whereas the activity coefficient are less than 1. And similarly, now your XY diagram will have first a convex, then change to concave, but you still have this XY equilibrium curve still cross the 45-degree line. Okay. And as you change the operation pressure, the azeotrope point will change. Okay, that's very a lot to see. Just some concepts, so you know that there's such azeotropic system that exists. So next, we're going to talk about multi-component flash calculation. So, so far we've talked about two-phase system, right? Vapor, liquid, two phases, right? And we talk about binary system. We have in our liquid or vapor phase, we have component A and B. But now we're going to move on to a system with more components, right? More than 2 components. So this process is called flash because typically we have a liquid phase, right, made of many components, and then we can partially vaporize it, right, by either adding heat, increase its temperature, or reducing pressure by using a valve. Then we will produce vapor, and this process is called flash, and this separation unit is called flash drum, right? And if the relative volatility of all the species in our fate is large, then we can do a good separation in one step in a single stage process. But if the relative volatility is small, then this operation is typically an auxiliary operation to prepare a fate for other further separation process. So there are two modes of flash, right? Either we can partial vaporization, right? That's when we start from a liquid stream. We can also do a partial condensation. That's when we have a vapor stream. There are isothermal flash. That's when when we have liquid stream coming into this flash drum, right? And if the liquid phase partially vaporized, because we know that vaporization consumes energy, and if we don't add energy into the system, then temperature will drop, right? But if we add energy into the system, we can maintain the temperature in the flash drum to be the same as a fate temperature, right? T equals TF, and this type of flash is called isothermal flash, right? But in order to maintain this condition, then Q needs to be computed, because the duty of the heat exchanger needs to be computed. There's also a adiabatic flash. That is to say that we don't care about the temperature change in the flash drum. We just operate the system without adding or removing any heat. So the system is adiabatic. Q equals 0, but the T will be different from TF, right? If we have a liquid stream and we partially vaporize it, then T will be lower than TF, right? Whereas if we have a vapor phase and we condense it, then we will have otherwise. In this case, T is unknown, so it's kind of more difficult than the isothermal flash. So next, I'm going to introduce the Rachel-Rice equation, right, which is an equation for us to analyze multi-component flash process. Similarly, we can start from the number of variables and number of equations we have for this multi-component system. We've done this before, so very simply, we have a composition for the feed, the liquid phase, the vapor phase, and we have the flow rate FLV. We have the temperature and pressure for the feed, and for the flash drum, and we have the duty of the heat exchanger. That gives us a total of 3C plus 8 variables. And we have species mole balance, right? They give us C equations. We have phase equilibrium, C equations. Then we have the mole fraction sum to 1 for the vapor and the liquid phase. And we have energy balance. But one thing that is different from the previous slide is that instead of having summation of Zi goes to 1 equals 1, we don't include that equation here, as you can see. Instead, we have a total mole balance equation here, right? So total number of equations are the same. The conclusion will be the same, but now we just change the condition a little bit. And these two equations are actually equivalent, right? So basically, let's say if we don't have this equation, we have the summation of x, summation of Zi equals 1. Now what you can do is just sum this equation over all species, right? Then you will find out, well, summation of Zi is 1, summation of xi is 1, and summation of yi is 1. You get f equals L plus V, so that's this one, right? Okay, so they are equivalent, but we don't include that equation because they are not independent condition, right? So because you have one, you can derive the other. They don't provide unique information, so we only include one. So we'll have similarly, the degrees of freedom will be the difference between the number of variables and number of equations. That'll be about say plus 4. And then for the Flash calculation, multi-component Flash calculation, we typically know Zi, Tf, Pf, right? That give us 2 free variables, right? Zi give us C knowns and T plus P. That's 2, and we have 2 free variables. But now you may ask, well, previously we talked about we don't give all the Zi, right? We only give C minus 1 of Zi's. But why we give all Zi's here? Any guess? I mean, still, that's because, in the equations, we don't include Zi's summation of Zi equals 1, right? Instead, we include this one. So you can assume that we cannot do that. So we have 2 free variables. And also, I mean, in this set of equations, we have K, we have HF, HV, HL. These are used as parameters with whose values are known. Instead, so they are not treated as variables, right? They are treated as parameters, whose values can be computed based on the value of all the other information, right? For example, we know that P value is a function of temperature and pressure and the Y and XI, right? The key value can be computed by the de Broglie equation if you know the temperature and pressure, or can be computed by using the Anton's equation plus Raoult's law if you know the temperature and pressure. And enthalpy for the feed and the exceeding and the exceeding vapor in the liquid phase for sure will depend on the composition and their own temperature, right? So we have 2 free variables. Now let's look at further drill down this equation. Now, well, we've done the Q line, and as you can see, the Q line method is really we have a whole set of equations, right? But we don't want to solve all of them. So we try to combine the equations to reduce the number of variables, right? In the Q line example, we kind of reduce the number of variables to only 2, which is Y and X. And then we can just plot the Q line on the XY diagram, right? Then graphically that helps us to find the solution by finding the intercept of the Q line with equilibrium line. So here we're going to do the same. We're going to do something similar, right? So we try to reduce the number of equations, kind of to simplify the problem a little bit by combining some of the equations. So first thing we do is that if you combine the first 2 equations, right? So we have Yi here, and we have the Yi can be computed by the phase equilibrium. If you plot Yi here, if you replace this Yi by Ki Xi, right, then you just eliminate Yi. Then you rearrange this equation, right? Put X on the left, and put all the parameter of X on the right. You get this. So Xi now depends on Zi, F, L, V, and Ki, right? Now we know that from the total mole balance, that's this equation. F, V, and L, they are interdependent, right? So then we can eliminate L, right, by, from this equation, L equals F minus V, right? So you replace L with F minus V, right? And now we further eliminate L, we further, reduce one parameter in this equation. Then you just do some organization, right? So divide F on both the numerator and denominator, you will have Zi equals this, Xi equals this, right? Now you see Xi is only a function of Zi, Ki, and this is the mole fraction of vaporization, right? Which is, kind of something we can control. Similarly, then you can just use this equation, like Yi is this Ki multiplied by Xi, you get this. Okay. up to now, we have used this equation, and this equation. We have not used these two equations yet, right? Let's see what we can get if we further use those two equations. Well, to use those two equations, it's just simple. We just need to, because now we have xi and yi, we just need to sum xi and sum yi over all components, right? And that will give us 1. And if we subtract them, that should be 0, right? That's what we have here. So this is the summation of yi minus summation of xi equals 0. So we define this is C. I don't know how to, what's this Greek symbol? Psi? Psi, right? Yeah, well, let's call it psi. I mean, doesn't matter. Psi, let's say we define psi to be the mole fraction of vaporization, that's V over F. Then we can get the Rachel-Rice equation, right? So basically, the summation of this term equals 0, right? And in which we have, Zi, Ki, and psi. Well, we have only 3 variables. And typically psi is known, which is something we can control. And Ki is, well, we don't have 3 variables, we have 2 variables because Ki is a parameter, right? So we have only Zi and psi, right? So now we have one equation with 2 variables, psi and Zi. Well, not 2 variables. Zi is C variables, right? So C plus 1 variables, and psi can be controlled in the process, right? So now let's see what we can do with this equation. It seems like we kind of simplify the whole equation set to a great deal, and let's see what we can do with it. And the simplest case is that if we let psi at the bubble point and the dew point, we know that at the bubble point, that's when we kind of like we heat up a liquid mixture to the point, the first bubble. I mean, to the point the first bubble comes out, so the liquid becomes saturated liquid, right? Now it enters the equilibrium region, but the vapor ratio is 0 because we just formed the first bubble. So that in that case, psi is 0, right? So the flow rate of vapor is 0, so L equals F. Psi is 0. Psi is V over F. Now, if you plug in this condition, right, psi equals 0 into that, this term vanishes, right? So and this is 1, so we can just ignore that. And we have Zi, Ki, and if you put Zi into these brackets, so you have Zi multiplied by Ki minus sum Zi equals 0, right? And sum Zi is 1, right? And if you move that to the right, you have sum of Zi, Ki equals 1, right? Now with that, because we know Ki is a function, Ki is dependent on the temperature and pressure. So in this case, if we fix pressure, then we can find the temperature. We can find one temperature that satisfies this equation. That's the bubble point temperature, right? And for the case in which if we use Raoult's law to correlate, P value with the pressure, you can just plug in the P into this equation. You will get the P bubble to be the summation of the Zi multiplied by saturation pressure, right? So at the dew point, we have liquid phase flow rate to be 0, right? So which means V over L is 1. But in that case, if you plug in the number, this is 1. And if you do the math, you will find out we're going to have the summation of Zi over Ki to be 1, right? Similarly, right, this equation may look different, but we can solve this using similar method, right? So for a given temperature, you can find a temperature, for a given pressure, you can find a temperature, right? At which point the Ki value of each component make this equation satisfied, then that will be the dew point, right? And similarly, you can do this with the pressure. So again, if we need a model for the key value, and if we use the Raoult's law as a model, then this is the kind of the simplest case. You can just plug in Ki here, then you will get the dew point pressure to be this. Now let's look at more complex case. Let's say if we don't use Raoult's law, because Raoult's law is so simple, because if you can just plug in the numbers. What if you use other models in which the key value does not dependent on the temperature and pressure in a very simple way, right? If the key value depends on temperature and pressure in a nonlinear way, and what you can do here is that to solve this problem, to find out the bubble point and dew point, what you can do is do iterations, right? You start from let's say if we have a given pressure, we need to find the bubble point, right? Then to solve this problem, we just need to find a key value that satisfies this equation. And to do this, basically you start from a guess, right? You can guess the temperature, right? Then now you know the pressure and temperature, you can compute the key value based on your model. Then you plug in the key value into this equation, you will get summation of Zi equals Ki, right? And it's not necessarily 1, it could be 10 or 100, right? Which is different from 1, which means this temperature is not the bubble point, right? And depending on if the summation of Zi Ki is larger than 1 or lower than 1, then you can, just change the temperature, right? You can reduce the temperature a little bit. That's your second guess. Then you plug in your temperature and pressure into the model for computing the key value. Then you get the key value, you plug it back here, you compute the summation of Zi Ki again, and you compare the result with 1. And you do this, iterate by iterations until you find a temperature that gives you a key value that satisfies this equation to a reasonable extent, and that will be your bubble point. Right, this is how you do it. Manually, you can do it by hand, right? Just do it multiple steps. But now I know you guys can do it in Python. You can just write down an iteration code and do this, automatically. Okay. So and I mean, if you do have questions about how to do this using the Python code, come to see me in my office hour. I can give you some extra information. At equilibrium, the vapor is at its dew point and the liquid is at its bubble point. So this is just one example. Right? So in this example, we have a mixture of butene isomers and the pentane isomers, right, at the known composition. So how do we find out the bubble point and dew point of this mixture? Right, that's just what I described. You can just solve this equation to apotential T. You start from a model, right? We can use the de Prystor model, and you guess, and you make a guess. You plug in T into this de Prystor correlation. You get key, right? And note here, temperature is the unit of temperature is Rankine. The unit of the pressure is PSI, so it's not standard units, right? So you plug in, you get the key value. Plug in back here. See if it matches 1. If not, do the situation.
With that correlation, is that pressure the system pressure or the partial pressure?
It's overall pressure.
Overall pressure, okay.
Overall pressure. So you can also compute the equilibrium diagram, right? That's a little bit more complex than the previous example, but we know that the equilibrium diagram is just made of many dew point, just made of like the dew points temperature and the bubble point temperatures at different composition, right? So what you need to do is just start from one composition, compute the bubble point and dew point, you get 2 points. Then you move on to the next composition, do the same, you get 2 points. You do this until you have enough points that give you enough confidence to draw a line that connects all the points. Then you get an equilibrium TXY diagram, right? So I mean, still conceptually it's the same, but maybe numerically it takes some time for you to do this. But if you can write a algorithm to do it for you, then it shouldn't be that difficult. Any questions? Okay. Okay. If no questions, I guess we can stop here, and I will see you after the spring break. Enjoy your spring break.
So on the calendar, it says it's due the Monday after spring break. But there hasn't been one posted yet.
That's homework, how much? 5?
Yes.
Let me take a look at the syllabus. Okay, so in that case, I think what we've done is homework 4 deadline has been posted to today, right? That's been official on Canvas. So homework 5 will be posted 1 week after 1 week after we come back from spring break. Right? It's not the first day you come back from spring break. Like it's like because we already postponed homework 4, we might as well postpone homework 5 so that you guys have enough time to work on the problems. Meanwhile, I want to make sure that you have time to discuss and I mean, if you have questions about homework, I want to make sure you have time to discuss with your peers and come to my and TA's office hour before you submit homework. So that it's not official yet.
Okay.
But we've decided to do that. So TA will, when they post the homework, they will make that change.
Okay.
If not, just send me a message to remind me. Okay.
Okay. Sounds good. You. Is that yours? Okay. You're good. Started making great tea, but I'll never get one. Oh, God, who Sam's go to? Yeah. Your favorites. Love exam days. They don't destroy like that. They destroy your exam. Also, this Tuesday, if I need to go. Send me message or send me an email. I will forward that to GA. So when because you're going to do a slate submission, but if you do that, we can make sure that we don't cut any points from the email. And how much time do you need?
I mean, I think I know how to do everything, and I have the roadmap, I just have to build it. So that's, I think maybe a day.
Sure. Yeah, so let's be reasonable. So and we cannot extend too much, right? I just because we're gonna post the homework solutions, right? If we delay this too much, it just make it difficult. So maybe by next Monday.
Okay.
Okay.
Yeah, sounds good.
So give you 2 extra days to do.
Okay, thank you so much.
Okay, no problem.